Once around, Stephenson 2-18. So what is this story all about? Well, Stephenson 218, also known as Stephenson DFK1 for reasons I'll explain in a moment, is possibly the largest star in the universe. It's an extreme red hypergiant star, at least according to many of our studies. As a red giant star, red supergiant, red hypergiant, it's in the final stages of its life and is liable to explode at any moment and leave behind a black hole. Very interesting object indeed, located in the southern constellation of Scutum, one of several massive red giant stars in open clusters, large open clusters in this part of the sky that contain a lot of these objects. And in fact, one of the clusters is called Stephenson 2, marked inside that black square on the right of the diagram there. Sometimes these are called RSGCs, red supergiant clusters, and this is sometimes called RSGC2, but Stephenson 2 named after Charles Bruce Stephenson, the astronomer who discovered it in the 1990s using deep infrared data. And you can see in the image actually that we can't really see a star cluster at all because there's that huge swathe of black, dirty, dusty material blocking it in the optical. But with the infrared, Stephenson was able to see through that and make some interesting discoveries. The brightest star that he found in his infrared images, he numbered 1, but realised later perhaps that it was an outlier on the edge of the cluster. Perhaps that was making it easy to identify. It's abnormally bright compared to the others in the cluster and moving in a different way. So it's been reclassified as an unrelated red supergiant. A later study gave it the designation 18, so we now had two names for this, Stephenson 2-1 and Stephenson 2-18, and they even thought that it might be part of a separate cluster, Stephenson 2SW, which stands for Southwest. So now it's been given the new name Stephenson 2 DFK1. On the grounds that this will avoid confusion. But it hasn't, because people just can't make their mind up. So a paper by Humphreys talks about it and assigned the name, the moniker, RSGC1-01. So this is yet another name for the same object, although there was already an object named that, which was a different star in a different supergiant cluster in Scutum. So got to be careful with this. Things have got totally confused. But anyway, Stephenson 2-18, as I'm going to call it, because there is only one object that's used that designation at least, is a long way away. 398,000 light years, perhaps, was the original estimate. But now that's dropped by perhaps a factor of 20 to around 19 to 20,000 light years. A big change. The distance is based on the apparent brightness that we see and measure and the luminosity that we think the star should have. And the luminosity is estimated from the temperature, and the temperature is estimated from the shape of the spectrum. Stars shine because they are hot, and hot things give off what we call black body radiation, which has a particular distribution of wavelengths and frequencies of different energies, with fewer of the high energy, a bulge at the maximum peak corresponding to the temperature, and then a long tail into the low energy infrared radiation. And so if we can look at the spectrum and plot the curve, we can fit that onto the black body radiation curve that we know and understand, and that tells us how bright, how it tells us what the temperature is. From the temperature we can estimate how bright the star should be, and from how bright it appears to us, we can use the standard candle rule and the inverse square law of distance and allow for other assumptions like intervening dirt and dust and get ourselves an estimate of the distance. But I think you can see that in that sort of chain of reasoning there are quite a few things that could go wrong. Now, I mentioned that we're not sure whether or not it was part of the original cluster Stephenson 2, and the reason for that is that in looking at the spectrum you can also see the spectral lines of absorption and emission in the light coming from the star, and from that we can work out what it's made of, but we can also tell the Doppler shift, the red shift or blue shift, depending on whether it's moving away from us or towards us. And S218 is moving away from us at 89 kilometers per second, whereas the other cluster stars are moving 20 kilometers per second faster, doing 109. And that missing 20 kilometers per second, kind of initially people thought that's proof that it's not part of the cluster. But what we think might be happening is that this very massive star is puffing off or radiating furiously and driving away its outer envelope, and the outer envelope is moving out from the star in every direction, and of course the bit we can see is the bit that's between us and the core of the star and is coming our way. As the radiation pressure forces it away from the core, it's coming outwards and towards us. And the typical expansion rate for such an envelope on a massive star like this would be around 20 kilometers per second, in which case the sums all add up, and so perhaps S218 is part of the cluster. The other grouping that was assumed was this Stephenson 2 Southwest, and that was in the end assumed to be at the same distance as the main cluster, containing a whole lot of other red supergiants, including a very interesting one, Stephenson 2 DFK 49, to use the DFK nomenclature. And so it doesn't really matter whether S218 is part of one cluster or the other, because we think they're both at the same distance from us. So physically, one of the largest stars we know, a red supergiant or even a red hypergiant, depends on your terminology really, a very big star, possibly the biggest star in the universe, much bigger than the Sun, much bigger even than UY Scuti, which was a previously detected very large red giant star, and even than YV Canis Majoris, which used to be the record holder. So absolutely enormous. If we compare it against the Sun, you can see that tiny little pixel there labelled with the Sun and the corresponding size of Stephenson 218. 2,100 times the diameter of our star. If it was in the middle of the solar system, it would go all the way out to Saturn. Absolutely enormous. Now, again, we can measure the temperature and we find that it seems to be 3,200 Kelvin, and we can estimate the brightness and we get 440,000 times the power output of Sol itself. Now, that's all well and good, but these sizes are breaking the theoretical models. We have our models that suggest that the most powerful you could have and the largest red supergiant shouldn't be bigger than 1,500 times the diameter of our Sun. So 2,100 is too big. So it's making life difficult for the modelers there. Now, it could be that we've got the brightness wrong, or that we've got the temperature wrong. We've probably got the temperature right, but maybe the chain of reasoning about the size and brightness is what's letting us down there. We think it's a very massive star, somewhere in that range of 30 to 50 solar masses. So not the most massive star in the universe. We have seen some that are over 100 times the mass of our Sun. And certainly getting old, for its size, somewhere in the range 14 to 20 million years, and stars of 30 to 50 solar masses only last about that long, so no surprise that this is in its red giant phase, where it is reaching the end of its life. Again, you can see the tiny little dot of the sun there marked just for scale. Now, those brightness estimates, in 2010 they estimated the distance at 18,000 light years and a luminosity of 90,000 suns. 2 years later, they've come out with a new figure which has given us 440,000 times, and most recently 630,000 times, because the distance has been increased again. So there's a lot of variability in these estimates, but it does seem that it may well be obscured by more reddening dust than we thought, and so may be an absolute monster. If it is, and the age estimates are right, then it's due to die anytime soon, and very, very likely to explode as a supernova and directly form a black hole in the core. It's so big that it won't stop at forming a neutron star. It will create a black hole directly. And along with that, it's very much on the brink. There's a lot of material being ejected. We've already seen that in the estimates of the radial velocity of the ejector coming towards us. But as it's losing mass at an incredible rate, puffing off these outer layers of very, very tenuous but nevertheless hot material, ejecting it into space, it's going to evolve, and it's not clear whether it's going to blow up or become what's called a luminous blue variable, a blue giant star that pulsates, having lost all of the hydrogen from its outer layers. You get helium as the next element that was made in an inner shell exposed, and these very high temperature helium stars tend to pulsate and become variables, luminous blue variables, or even Wolf-Rayet stars, where they continue to lose enormous amounts of mass. And I've done another video all about Wolf-Rayet stars if you're interested. So as I said, the temperature 3200 Kelvin is calculated by looking at the spectrum, and you can see the spectrum at the top there. We have the flux versus the wavelength, and you can see lots of different spectral lines from iron, from titanium, from calcium, other elements are all in there. Very high resolution spectrum. So we learn a lot from that, and we can use what's called the Dusty computer model. These things have to have a good acronym to try to understand the temperature, and that's where we get the 3200 from. But that's too cold. It's cooler than the coolest other red supergiants that we see and are predicted by our understanding of the theory. So again, this one is definitely bending, if not breaking, the theory somewhat. And the explanation is that maybe it's not yet fully finished forming. So maybe this is still quite young, very massive star indeed, burning very fast, and although it appears to be dying around the outer layers, giving off all that material, it may well still be settling in the centre with the denser material sinking within. So when we try to look at these possibilities of these very young stars, something that has been noted by Japanese astrophysicist Hayashi is a thing called the Hayashi Track, and this is on the Hertzsprung-Russell, the HR diagram of temperature versus luminosity. You get that diagonal line which corresponds to the bottom right hand corner for little red dwarfs at 0.1 solar masses, up to the middle sun-like stars at 1.0, and then up here we've only gone as far as 6 solar masses on this particular chart. But what happens is that as stars form, they don't magically appear on that diagonal, on that main sequence, they start towards the up and right a bit, where the envelope of the coloured lines is limited. And at this stage they're protostars or T-Tauri stars that are radiating energy released from gravity, even if they haven't yet kicked off nuclear fusion. So they have an extra boost of gravitational potential energy as they shrink and differentiate, and the denser materials sink into the centre and so forth. So they end up being a bit too bright for their mass, and so they sit on this upper track, and then as they shrink they move along that track down along the blue lines onto the correct position on the main sequence as they mature into the ordinary hydrogen burning stable phase. So as they contract, the temperature tends to remain fairly constant, particularly for the small ones, and that drives them vertically down the diagram from the upper red lines to the later main sequence at the bottom of the diagram. As the mass goes up, that line takes a slightly different course and ends up being more horizontal with a little kink in it. So we think we understand all of that. And the problem is that Stephenson 218 doesn't seem to fit, because you notice that the larger the mass of the star, the hotter it tends to be, the brighter it tends to be, with those solar masses up there at 5, 6 or even greater, all being at the top left-hand side of the diagram. And the temperature in thousands of Kelvin along the bottom there goes from just 4.4 to 3.5, which is the bottom end of things. It doesn't go any further, so 3,200 is off the chart. You're actually in what's called the forbidden zone. And we've got the equation there for the amount of energy, and you can see it's interesting in that it involves 4 pi g, Newton's constant that tells us about gravity, mu over k h, which interesting parameters, the mass, the radius, the pressure and the temperature all factor into it. So what we get is this forbidden zone, and really it all goes back to that Stefan-Boltzmann law, which I've talked about. This is the law of the radiation of energy from an object based on its temperature and its size. So L, the luminosity, the brightness, is 4 pi r squared, where r is the radius, times the temperature to the 4th power, and times that little constant sigma there, which is just a constant to get the units correct. And so it's proportional to the 4 pi r squared, which is the surface area of the object, and the 4th power of the temperature of that surface. And that's how, if we know the temperature and the luminosity, we can work the size out. We know T and we know L, and then we can work out how big something must be, or if you know any two of the others, you can get the third one. But this Hayashi Track, again, separates us into the allowed region, where we're towards the left, higher temperatures and smaller radii for each given luminosity, and the forbidden region of low temperatures and large radii. Clearly, if you are going to have the same luminosity, if you lower the temperature T, then the radius has to be bigger. And Stephenson 2-18 is in the forbidden zone. So something very, very strange is happening about it. Now, I talked about the mass loss as it's losing all of that outer layer, blowing the hydrogen away. Works out to be a solar mass every 80,000 years being blasted into space. And this too is a record holder. It's the highest known for any red supergiant. And there's a possibility that there's been a recent outburst in human timescales, not observed by anybody because this is so far away and hard to see, but maybe there is a thick ring of dust that is accounting for a lot of our problems here. So that's one possibility. It's also doing something that some of these other red hypergiants and supergiants do, it's emitting microwave laser light, masers. These were first detected from space back in 2012 as water-based masers, so water molecules in and around the outer reaches of the star being energized by the power of electromagnetic radiation and the magnetic fields coming away from the star, and caused to fall into lockstep in this stimulated emission of radiation, which is, in the case of light, laser stands for light amplification by stimulated emission of radiation, and here it's microwaves, so maser. Actually something that Einstein predicted. He got around, didn't he? And it seems to be in this envelope of the star that this maser effect is coming away. And not only have we detected water, but also silicates, so sandy, rocky material giving off these particular wavelengths, 10 micrometers, 18 micrometers, maser radiation. And so this provides another way of studying it. And the fact that there's so much silicate, so silicon and oxygen present in this material, this is stardust, this is dust being emitted by the star, showing that actually it's got quite large quantities of those heavier elements in it, again pointing to imminent death. So a fascinating object indeed, this red, I'm going to call it a hypergiant. There's still that doubt, and we need to know more. It's always the case for a lot of these objects that the more you delve into the astrophysics of what's going on, the more you find that there are things that we just don't know yet. One of the things I love about astronomy. So I'll leave you with a picture of the red hypergiant, Stephenson 218, and thanks very much for listening to that one.